Section 4, Driver and Monitor Objects. Let's focus on the sequence and driver objects. They're shown here as part of the environment module, the top-level module where all the objects are constructed. That happens in a UVM-like task called build. As we've seen, the sequence sends randomized transactions down to the driver in the form of these data packets, and the driver extracts the different fields, the tag, the frequency, the mode, and applies those values over the lines of the gray-clad interface bus, which in turn connects with the fixture port freak in. But how does the driver, an abstract class, connect with a hardware interface bus? The answer is we use a virtual abstraction called a virtual interface bus, symbolized by this diamond icon. Let's see how it works. Slide 39 shows part of our driver class code. This is only the portion where we set up the virtual interface variable or property of the class. Let's call it vdiff. Here we declare it, and it almost looks like we're instantiating a copy of our interface bus and calling it vdiff. If we did that without this virtual keyword, we'd get an immediate syntax error because you can't instantiate hardware like a logic module or an interface bus within an abstract class. But by declaring it virtual, we make this an abstraction. So at this point, we've declared our virtual interface variable vdiff, but it's still null valued. It's a pointer to nowhere. We need to assign it a value either procedurally or as part of a constructor function. Let's do it in this new constructor function. When driver is constructed and its new function is called, an actual value will be passed into this formal argument diffarg, and this argument is just the right data type to assign values to vdiff, our virtual interface. Where does the actual value come from? Well, let's switch scope and look at part of the build task in the environment module. Here's where we're constructing a driver object drv by calling its new function that we just saw. And we're passing in an actual value diff, which is the instance name of our hardware interface bus. So we've just made the connection using the virtual interface bus vdiff. We can now access signals on that bus. Let's dig deeper into the driver class code. Here is the main task, apply sign. And as you can see, it loops over some number of trials, just like the sequence object did. On each pass, we create a new transmit packet ready for transaction data, and we stuff it with that data by calling the get method on the mailbox coming down from the sequence object. So TX packet has now been filled with the frequency and mode for this transaction. The driver must be aware of DUT-level timing details. We've chosen to apply new stimulus at the very beginning of each new clock cycle on the rising edges of packet clock. So here you see at that point in time, we're applying each field of the packet to the corresponding signal bundled into the virtual interface bus vdiff. So we've driven the transaction values into the DUT. Before we wrap up this apply sign task, we want to take that same transmit packet, which we've read but haven't altered in any way, and we want to put it into another mailbox connecting the driver on up to the scoreboard. And there we can evaluate the results. Let's turn our attention to the monitor class. It's organized in a very similar manner. It has its own virtual vmif bus. So we'll just focus on the main monitor method sample PPA. And on each iteration of this for loop, it creates a new ready-to-use receive packet. And remember, the monitor is doing the reverse of the driver. It's taking data coming in on the interface bus, the virtual bus VMEF, namely the peak-to-peak amplitudes in and out of the filter, and assigning those to the corresponding packet fields. Thus, it reconstructs the packet. And at the end of this task, it puts the entire packet into this mailbox, connecting the monitor on up to the scoreboard. One more key statement. The monitor includes a coverage group named CVG, which we'll use to gather coverage metrics. And we'll see the code in section 8. The key point here is that now that we've applied a transaction and are certain it's been successfully used and we've got a valid amplitude coming out of the filter, we call the sample method on the coverage group, collecting more metrics data. And so the monitor has reconstructed the packets, sent them on up to the scoreboard. Oh, the timing is important. Here we're sampling the filter outputs roughly in midway during the clock cycle. We're using the signals tick and tock, which are triggered by falling edges of packet clock. And the difference between tick and tock allows for this yellow highlighted dwell time, just enough time for accurate measurement of a peak-to-peak sinusoid amplitude. And so we've sampled the peak-to-peak values at this point. We added a small sample delay, just a few microseconds for the 1 or 2 time steps delay in some of the X model primitives. So at this point, we've sent both transmit and receive packets on up to the scoreboard. And in the next section 5, we'll see exactly how the scoreboard computes the actual filter gain and the expected, and then compares them together.